Good morning, students. Last time we have spoken about what we call as the different compounds of or the different oxides of nitrogen. And with respect to the oxides, we spoke about the different compounds of nitrogen. One was ammonia. We spoke about its method of preparation of ammonia with respect to Haber's process. And then we have also spoken about phosphine, that's pH3, all right, and its properties. Now, the next part, what we have with respect to phosphorus, a very important part, that's its halides. So we're going to talk about the different compounds of phosphorus, in which two halides. We have discussed about this, if anybody recalls, in chemical bonding, PCl3 and PCl5. Let's start this. PCl3, first of all, if I have to tell you, phosphorus over there, when I'm saying atomic number is 15, so it's neon 3s2 3p3. So if I write the electrons with respect to the Hund's rule, it's going to be a lone pair in the 3s orbital and 3 unpaired electrons in the 3p orbitals, that is 3px, 3py and 3pz as per the Hund's rule. Now when it forms a compound like PCl3, what exactly happens? With PCl3, phosphorus will combine with 3 chlorine atoms. So the hybridized state is sp3, similar to ammonia, where there is one lone pair, and that's what you rightly see in the structure over there. So if I have to tell you with respect to the part, like for example, if you see this lone pair, everybody over here, so this is the lone pair of phosphorus that is in the 3s orbital, and here are the 3 chlorine atoms at the 3 corners of the pyramid over there, that way. So it's a what we call as sp3 hybridized, a pyramidal geometry, where the PCl, all right, if you see the down diagram, that's around 204 picometers, and the bond angle is around 100 degrees because of the two types of repulsion, that is lone pair bond pair as well as bond pair repulsion. That's one. Second, moving now, what we have over here is, what if I have to tell you, is with respect to, now coming to its method of preparation. Okay, phosphorus combines with chlorine, it forms PCl3. That is one part what we have. And second is, phosphorus also combines with SOCl2 to give you PCl3. Now what is SOCl2? SOCl2 is called thionyl chloride, which is S double bond O and 2Cl on the two sides. That's thionyl chloride. When we do organic, in halogen derivative, there is a method of preparation or of alkyl halides from alkyl chloride, specifically from alcohols, called Darzin's method. DARZEN, Darzin, okay, not Tarzan. So in Darzin's method, we use SOCl2 to convert alcohol to alkyl chloride. So that's SOCl2, thionyl chloride. Properties wise, people, it hydrolyzes in the presence of moisture, meaning PCl3 with water in presence of moisture from air, it will break down to form H3PO3. Now what is H3PO3? It's one of the oxo acids of phosphorus. This we'll be doing in the next class. What's an oxo acid of phosphorus? Oxygen containing acid with phosphorus. That's H3PO3, what we call as phosphorus acid. Us means the oxidation state is lower over there. So if you see over there in H3PO3, if I have to tell you the oxidation state, phosphorus is in +3 state. That's one. And second, in organic, when we do the chapter aldehydes, ketones and carboxylic acids, in derivatives of carboxylic acids, if you recall organic, when we did nomenclature, we did 3 different derivatives of carboxylic acids. One was acid chlorides, COCl group, called alkanoyl chloride. CONH2, that's called acid amide, alkanamide. And third was C double bond O and then again O and then O and C double bond O, which was an acid anhydride group, what we said. So that's alkanoic anhydride. Here we have preparation of its derivatives there. So look at this. Acids, when I'm talking, just please see the slides over here. This is carboxylic acids, the OH group. When it reacts with PCl3, the OH is substituted by Cl. That's what you rightly see. So this reaction is what type of a reaction? It's a nucleophilic substitution reaction. Substitution because single bond, CH3C double bond O, that double bond O remains as it is, OH is removed and it's substituted by Cl. CH3COCl, common name, acetyl chloride, IUPAC, ethanoyl chloride. That's the one. And the byproduct, that's what we call as H3PO3, phosphorus acid, or we also call it as orthophosphorus acid. Ortho the acid which is most common. For them we put the prefix ortho also. So just phosphorus acid or orthophosphorus acid. And same way, alcohols, what I said method like just now for SOCl2 Darzin's method, there we have three things. Alcohols can react, Darzin's is specifically with SOCl2, but alcohols can react with PCl3, PCl5 as well as SOCl2 to give respective alkyl chloride. So that's the next reaction. Just have a look at this. In ethanol, so the OH is replaced by Cl. Okay, so if the OH is replaced by Cl, again this is nucleophilic substitution. So here we have converted ethanol to chloroethane. So two derivatives are prepared. Alcohol to alkyl halide using PCl3 and acid to alkanoyl chloride using PCl3. Okay, so both these reactions will come in organic also. So acetic acid, ethanoic acid giving us ethanoyl chloride, and second reaction ethanol giving us chloroethane. For both the byproducts and the balancing is the same. Alright. Now structure we discussed, PCl3 distorted tetrahedral. That's going to be like a pyramidal structure over there what we have, and it's sp3 hybridized. Alright. That's one. So that's PCl3 molecule. Next we have a compound that's PCl5, phosphorus pentachloride. Now PCl3, if I have to classify, alright, what will you classify? Electrophile or a nucleophile? PCl3 is a nucleophile. Why? Because it has a lone pair. So it's electron rich. So it will first have a tendency to donate its lone pair. Keep in mind, it has vacant d orbital also, but tendency is more to give the lone pair first and then its vacant orbital. So PCl3, anytime a question comes, example wise, it is classified as a nucleophile. Now for this preparation, that's with excess of dry chlorine. So phosphorus with dry chlorine will give us nothing but PCl5. And second is called prepared by the action of SO2Cl2, where phosphorus combines to give us PCl5 again. It's a yellow powder. It hydrolyzes to give POCl3 and finally it gives phosphoric acid. Previous part what we had, PCl3 when it is hydrolyzed with moisture straight away it gave you H3PO3. Here PCl5 first gives you POCl3, that's called phosphoryl chloride, and that phosphoryl chloride again combines with water to give you H3PO4. Now very important, H3PO4 phosphoric acid, or we also call it, it's a very common acid, so we can also call it as orthophosphoric acid. Here phosphorus oxidation state is +5, and if anybody remembers, in between in the class I had given you the structures. How you write H3PO3? P double bond O, left hand side 1 OH, right hand side 1 OH, and down H. So basically P double bond O, POH, POH, and down a PH. So it has got 2 OH. So the 2 OH explains its basicity, meaning the number of replaceable H plus ions it gives. So H3PO3 is a dibasic acid. When dissolved in water, it will give 2 replaceable H plus ions. What about the pH bond? Will it break? No. That pH bond explains its reducing nature. Reducing nature, which means it readily undergoes oxidation. So remember, the ionizable one, which explains its basicity, that is the number of replaceable H plus ions. Okay. Why do we use the word basicity? Because the replaceable H plus ions will neutralize how many OH ions? That explains its basicity. Okay. So H3PO3 has got 2 POH bonds. Both OH bonds, POH bonds will be ionized to give H plus ions. Whereas the pH bond explains its reducing nature. Alright. Come to H3PO4. P double bond O. 3 bonds. All the 3 are POH, POH, POH. No pH bond now. I repeat the structure. Please pen it down in a paper somewhere. Both are H3PO3 and H3PO4. H3PO3, P double bond O. Left POH, right POH, down PH. H3PO4, that's H3PO3 what I said. Now H3PO4, P double bond O, POH, POH, down also POH. So H3PO3 had 1 P double bond O, 2 POH bonds and 1 PH bond. Come to H3PO4, 1 P double bond O and 3 POH bonds. So as there are 3 POH bonds, I told you POH are the ionizable ones which gets ionized. So hence it will give 3 replaceable H plus ions. So H3PO4, the basicity is 3. H3PO3, the basicity is 2. H3PO3 is a dibasic acid and H3PO4 is a tribasic acid. Clear everybody? That's one. So here it forms H3PO4. H3PO3 lower oxidation state, so us plus 3. H3PO4 higher oxidation state plus 5, ic phosphoric acid. Now it says it sublimes, meaning when you just heat it, it will break down to give PCl3 plus it will give you chlorine. Alright, it's sublimation. Again, like what we said over there at organic, the same reaction what we had of PCl3, similar we have of PCl5. With acids, PCl5 will give alkanoyl chloride and alcohols will give chloroalkane. That's haloalkane. So look at this now. See the slide please. Alcohol with PCl5, the OH group is replaced by Cl. So again, nucleophilic substitution. Ethanol to chloroethane. And same way acetic acid, that's ethanoic acid, OH is replaced by Cl. So acetic acid becomes acetyl chloride or ethanoic acid becomes ethanoyl chloride. Alright. And secondly, it also reacts with metals where silver gets converted to silver chloride and PCl5 is reduced to PCl3 because PCl5 matlab higher oxidation state, same funda what we did in D and F block. In higher oxidation states, they are good oxidizing agents, so they undergo reduction. So PCl5, phosphorus is plus 5 becomes PCl3, plus 5 to plus 3 and silver which was 0 becomes plus 1. Understood? So higher oxidation state, good oxidizing agent, undergoes reduction. Lower oxidation state, good reducing agents undergo oxidation or increase in oxidation number. Similarly, people with tin gets oxidized to stannic chloride, 0, 2, plus 4. Stannous is plus 2, stannic is plus 4. Stannic is plus 4 and stannous is plus 2. And PCl5 gets reduced to PCl3. Coming to the structures now, PCl5 people we have done in chemical bonding, sp3 dehybridized, where that lone pair of the 3s also gets excited into the 3d orbital. So neon 3s2 3p3 becomes neon 3s1 3p3 and 3d1 in its excited state. So now there are 5 orbitals available. So 5 chlorine will overlap axially to give 5 covalent sigma bonds, where the 5 bonds, the arrangement is trigonal planar geometry, where 3 chlorine atoms, please just have a look at the structure please on the right hand side one. The 3 chlorine atoms, if you observe, are nothing but at the 3 corners of the triangle. That's making a trigonal planar geometry at an angle of 120. And you have 2 chlorine atoms up and down, that's called the axial bonds. That's at an angle of over there 90 degrees. Clear? Now a very important feature. Listen to this carefully. Please write it down somewhere. The important question. PCl5 is more reactive than PCl3. I repeat, PCl5 is more reactive than PCl3. Why? Answer is right on the board. Look at the left hand side diagram now. The 3 equatorial bonds are at a bond length of 202 picometers. Whereas the axial bonds, if you observe, that's nothing but over here at 240 picometers. That's what we have. Okay. Question is, technically, as per hybridization, the mixing and recasting should give rise to new orbitals all having the same shape, same size. Size is not same here. Equatorial bonds are shorter, axial bonds are longer. That makes PCl5 more reactive because if the bonds are longer, force of attraction is less. It can easily break. What's the logic of this? Answer is the repulsion. The 3 chlorine atoms, each halogen is NS2NP5. So NS2NP5 may say 1 electron takes part in bond formation. So there are 3 lone pairs. So as every halogen has 3 lone pairs, and if the 2 axial chlorine atoms also come closer, there will be lone pair repulsion. And due to the lone pair repulsion, what will happen people over there? Because of that people, that chlorine will not come closer. That's why the axial bonds are longer. So remember this, the axial bonds are longer to minimize interelectronic repulsions. Alright, so PCl5 is more reactive than PCl3. That's what it says here. Now just I'm highlighting some points. it says the three equatorial bonds are equivalent, matlab all have the same shape, same size, while the two axial bonds are longer than the equatorial bonds. That's due to the axial bond suffers more repulsion due to the equatorial bonds. That's the interelectronic repulsions. And it says in the solid state, it exists as an ionic solid, that is PtCl4 and PCl6 minus, in which the cation PCl4 plus is tetrahedral, whereas PCl6 minus is octahedral. Now people, this is very easy to catch. How? Look at the coordination number, PCl4 plus Cl4. So 4 bonds, chloride ion is a anionic ligand. 4 matlab tetrahedral. I have told you all, with coordination number 4, there are only two probabilities. Either it is sp3 or it is dsp2. dsp2 is generally with copper ammonium ion complex, what we spoke in D block, or platinum complexes, what we spoke in, what you call as chemical bonding part. Alright, so that's one. So 4 would be tetrahedral, and PCl6 minus 6 coordination number is always octahedral, either sp3d2 or d2 sp3 hybridized. Alright, that's one. Next now, alright, let's see some questions. Why does PCl5 fume in moisture? Now PCl3 fume in moisture because on hydrolysis it breaks down to give H3PO3 and it gives HCl. So the fumes are because of HCl. Okay, that's the part. Second, are all 5 bonds of PCl5 equivalent? Answer is definitely no. We discussed axial bonds are longer than the equatorial bonds to minimize repulsion. So that's the same thing. It's trigonal bipyramidal, that's sp3 dehybridized. 3 bonds are equivalent, the 2 axial are different than the longer bond. The reason we know, interelectronic repulsion. Then next, what happens when PCl5 is heated? Now when I say PCl5 is heated, we did it on the previous page. PCl5 sublimes to give you PCl3 plus it gives chlorine. And second part, hydrolytic equation of PCl5 in heavy water. If you recall heavy water kya tha people? Heavy water was deuterium oxide, D2O. So with D2O, PCl5 over there will form H3PO4. Alright, that's phosphoric acid. Okay. Heavy water, if anybody remembers, moderator which was used in the nuclear industry to slow down the speed of neutrons in the nuclear reactor. Okay. Now, this is one part. Now, the last part, people, what we have is the oxo acids of phosphorus. I'll just give a rough idea of this because this I'm going to take in a separate lecture with some shortcuts and tricks how I did for nitrogen of oxides, because this is a very important concept. You have to memorize them. So how to do it, that part we will see. Okay. Now, first of all, what are oxo acids of phosphorus? Oxygen containing acids of phosphorus. Phosphorus shows a variety of oxidation states. It moves from +1 to +5. Now in all these, depending upon how many oxygen atoms are there, we can talk about different oxidation states and how it forms. Now there is few catch. I want everybody to listen to this very well. Okay. Now in this oxo acids, one, in the lower oxidation states, that's below +5 oxidation state. Okay. What is the observation? There is over there a P double bond O. There is what we call as a POH bond. And along with this, so P double bond O is there, POH is there. Along with this, there is either a P single bond P or a P single bond H bond. Please write it down. In lower oxidation states, that is below +5, there is a P double bond O, POH bond. Along with this, there is either P single bond P or P single bond H bond, but both are never together, meaning in lower oxidation states you will never have PH bond as well as a PP bond. In higher ones only we will have lower oxidation state, but obvious people, as we know over there, what will happen? They will try to show disproportionation. Like for example, +3 can be increased to +5 or +3 can be reduced to 0 also. So they will disproportionate. That's what we will see. All right. And as I said, the POH bonds are the one which explains those are the ionizable bond which explains its basicity. In other words, it has how many replaceable H plus ions. And the pH bond, more the number of pH bond, that explains over there is nothing but reducing nature. Phosphorus generally forms 4 bonds. Why? Because technically, if I don't consider the d orbital in the beginning, in the ground state, it has got 1s and 3p orbitals. So 4 bonds it can form, matlab like a tetrahedral. So few just, as I said in lower oxidation states about the bonds. Second is the orbitals in the ground state. So 1s and 3 of the p. So it's a tetrahedral form what it forms. Third point, very important, in the higher ones, is this clear? What is the observation in higher oxidation states? In the higher oxidation state, the d orbital comes over there. So when the d orbital comes, there is what we call as catenation properties. Catenation means 2 molecules are fused and you get a higher compounds of an acid. That way, by removal of water molecules. That's what we will see. So in the next part, we discuss the oxo acids of phosphorus. That's the last part what we have of group 15. Okay. So most important, the anomalous behavior of nitrogen. Do that very well because that's important. Second point, the oxides of nitrogen, which I've explained. I hope it would be very clear. So please practice it once or twice so you are inside out with it. And third, this oxo acids of phosphorus. Okay, this I'll explain the next video to you so you'll get a very clear idea about it. All right. And then after that, next we start as group 16. All right. Thank you. Have a great day. Bye-bye.